Hello student. Uh, Polymer technology molecular architecture. In the previous class of the polymer technology, we talked about the introduction of the polymer, classification of the polymer and their applications. Now we will come to know how the polymer is architecturized. Architecture in the polymer science that is related to the way of branching leads to the deviation from strictly linear polymer chain, or branching may occur randomly. Reactions may be designed so that specific architecture are targeted. The way of arrangement of the molecules in the polymer structure is basically the architecture. So it is an important microstructural feature. A polymer's architecture affects many of its physical property, including solution viscosity, melt viscosity, solubility in various solvent, glass transition, temperature, size of individual polymer coils in any solution. You can see from this picture we have different shape polymer, different pattern of the arrangement of the crystals into the polymer. So this way of arrangement of the crystal is the polymer architecture. The first picture you see the block copolymer, and in the second this type of structure is called the star polymer, and this the third structure you can see that is called the comb polymer, and fourth in the right side is called the brush polymer. From the left you will see AB2 star. A is one molecule and B is another molecule. So two number of molecules of B. So this kind of arrangement can be said as a B2 star polymer. And next picture you see the palm tree. This is another type of structural arrangement of a polymer. That this type of polymer is called the palm tree polymer. You can see the structure is looking like a tree. Palm tree ABN means one molecule of a single component and another molecule for another component, n number of components of B. Next is H-shaped polymer, that is called B2AB2, means the two particles of the B component, one particle of A component, and again two particle of the B component. The shape is making like H shaped. So it is called H shaped polymer. Next is dumbbell bell, or it is called pom pom. You can see the pom pom structure. Next is ring block polymer. So this type of polymer is called the ring block, and then we have star block ABN. One molecule of A and n number of all molecule of the B. The structure is making like a star. Then we have coil cycle coil. So we have coil cycle coil. You can see one molecule is coming of A, then this is making a ring like of structure like a coil, and then another molecule is attached behind. So this is called coil cycle coil. Then next is star ANBN, n number of molecules of A and n number of molecules of B. So this type of polymer is called the star polymers. Now coming to the next slide, we will come to know how these molecules are being formed, how the different architecture of the uh, polymer is being generated. So now how the random branching happens. You can see the branches can form when the growing end of the polymer molecule reaches either a background onto itself. Either it reaches to the background on itself or onto another polymer chain, both of which via abstraction of a hydrogen can create a mid-chain growth site. Or branching can be quantified by the branching index. First is cross-linked polymer. So what are the cross-linked polymer? An effect related to branching in the chemical cross-linking. So molecules are linked crossly. So the formation of covalent bond between the chains. In between the two chains, there is a formation of one covalent bond at, at a single point. So at that point, the polymer is crossly linked. Cross-linking tends to increase strength and toughness in the polymer. Among other applications, this process is used to strengthen rubbers in a process known as the vulcanization. So vulcanization is the process of making rubber. So into this process, the polymers are crossly linked, which is based on cross-linking by the sulfur. Sulfur is a external component that is used for the cross-linking into the vulcanization process. Now another examples are car tires. For examples are highly cross-linked in order to reduce the leaking of air out of the tire and to tough their durability. Or you can see another example is eraser that you use in your stationaries. On other hand, is not cross-linked to allow flaking of the rubber and prevent damage to the paper. So into the eraser rubber, that is not cross-linked because this is not hard, very hard. This is soft. So polymerization of a pure sulfur at higher temperature also explain why sulfur becomes more viscous with elevated temperature in its molten state. Next type of structure is complex architecture. So the complex architecture is the molecules are arranged in a very typical way with the continual development of living polymerization. Synthesis of polymer with specific architecture become more and more facile. So architecture such as a star polymer, comb polymer, brush polymer, dendronized polymers, dendrimers and ring polymers are possible from the complex architecture. You can see at the right side the picture of a dendronized polymers. So these are the complex type of architecture. And at the another picture we have ABC. This is the example of the ring polymers. So complex architecture polymer can be synthesized either with the use of specially tailored starting compound by first synthesizing linear chains which undergo further reactions to become connected together. Or we have the example of the knotted polymer. The below picture you can see it looks like a knot of any thread. So it looks like a knot in a rope. So these kind of polymers are having the complex architecture. So this consists of multiple intramolecular cyclization units with a single polymer chain. Or another example is linear polymer may also fold into topological circuits. They make the network polymer. Formally classify their contact topology. So this is how the architecture of the polymer can be explained. So polymer of architecture of polymer means the way of arrangement of their molecules. And the next is molecular weight distribution. Now the how we will come to know into this how the molecular weight in the polymer is distributed. So molecular weight is one of the most central aspect of polymer properties. The number of enhanced monomer in an average polymer chain in a material is called degree of polymerization. So you can read this definition. The number of enhanced polymer in an average polymer chain in a material is called degree of polymerization. So this is a material you can see in the picture DP. So there are three structure of a polymer. So this mixture of a three structure of a polymer is a material, right? Into this, 1, 2 and 3 molecules of a polymers are there. So if you count the first one, we have uh, 9 number of molecules of units, repeat units, and then second we have 10 number of molecules repeat units, and the third one we have the 11 number of molecules in the repeat unit. So if you want to calculate the degree of polymerization, you add 9 plus 10 plus 11 and divide it by 3. So that becomes the average dp is 10. So when we speak about the polymer weight of a polymer, we are always talking about an average value. If there are three crystals, then we are talking about the average value of the uh, molecular weight of the crystal. So some chains in the material will be longer and some chains in the material will be shorter. So those who are longer have heavier molecule weight and those who are shorter will have the lighter molecular weight. So as with any group of measurement, it is helpful to know how widely distributed the individual value really are. In polymer chemistry, the width of distribution of molecular weight described by the dispersity. So dispersity can be denoted by this symbol D, also called the older text. In the older text, the polydispersity. Either it is called the dispersity or it is called the dispersity of the polymer. Polydispersity of the poly polydispersity index. It is called the dispersity, polydispersity or polydispersity index. So dispersity of a polymer sample is often between 1 and 2, or it can be even higher than 2. Once the molecules are closer, so it is called the value of dispersity will be near to 1. So into this we can say the polymer is narrower distribution. The distribution of the molecule is narrower. As you can see in the picture, narrower dispersity and wider dispersity. Into the narrower dispersity, you will see the dispersity of 1 would mean that all the chains in a sample are exactly the same length with the same molecular weight. In the second picture, the dispersity is greater than 1 or in between 1 and 2. You can see in the second picture, the blue picture, molecules, the number of molecule 1 2 3 4 5 6 7, and the second 1 2 3 4 5 6 7 8 9 10. You have 10 molecules and 7 molecules. Now this is 1 2 3 4 5 6 7 8 9 10 11 12 13 13. So if you add each and divide it by 3, means you calculate the average. So this average is becoming greater than 2, and this is uh, in between 1 and 2, and this is nearby 1. So this is the red molecules are called the narrower dispersity and the blue molecules are called the wider dispersity. So the origin idea of dispersity was based on the alternative methods of measuring the molecular weight or the chain length of a polymer sample. One set of method gave something called that number average molecular weight. So if you add the molecular weight of all and make an average, so that is called the molecular average weight, that denoted with the symbol mn. So these methods essentially took the weight of a sample, counted the molecule in a sample, and there found an average weight of each molecule in that sample. So a classic example of this approach is colligative properties experiment, such as freezing point depression. So if you weight a sample of a polymer, dissolve it in a solvent and measure the freezing point, you would figure out the number of molecules dissolved and consequently arrive at Mn. You can see how many number of molecules are dissolved with the presence of the solvent. So this molecular weight, total molecular weight is called Mn, average molecular weight is called Mn. So you can find out the dp, ratio of repeat unit to end group. You can see one molecule is connected with number of monomer units. Next is the ratio of those obtained monomers to the end group tell us how long the chain is, and the other set of method upon which dispersity was based gave something called the weight average molecular weight. The classic example was as light scattering experiment. You can see the picture, one light beam is scattered on the polymer crystal. So in this experiment, a solution of a polymer was exposed to a beam of light, and resulting scattered light coming from sample in different directions was analyzed to determine the size of polymer chain in the solution. So the result were more heavily influenced by the larger molecule in the solution. As a result, this measurement of molecular weight was always lighter than measurement based on counting every single molecules. So you can count every single molecule from the light scattering experiment. Now the next is resulting the ratio D equals to Mw by Mn. That becomes the polydispersity index. That's how the polydispersity index can be calculated. So because Mw was always more strongly influenced by longer chains, so it was a little bigger than the Mn, and therefore the dispersity was always bigger than 1. So that was the information about the polymer architecture and the molecular weight of the polymers. So next we will continue in the further lectures. Thank you.